Math 347 fans, welcome. Video where we see power of Laplace transforms in solving initial value problems. So we'll start this video by having a look at how Laplace transforms can be used on derivatives, and then we'll see how that can be used to solve initial value problems. And we'll keep in mind here, we'll start actually by looking at some initial value problems that we can solve with our methods from previous sections, and then at the end of the day here we'll see how the Laplace transform is powerful, especially when the source term, the f of t here, is piecewise continuous. Okay. So begin with a look at how the Laplace transform acts on derivatives. In general, what we'll see is that when our function x of t is nice, and again by nice we mean piecewise continuous and of exponential order, it turns out that we can find expressions for the first and second derivatives, the Laplace transforms of the first and second derivatives, in terms of the Laplace transform of the original function. So we'll start that with finding an expression for the Laplace transform of the first derivative. So this is the formula that we'll derive here. The Laplace transform of the first derivative is s times the Laplace transform of the function minus the function evaluated at 0. And just like before, when we're trying to find the Laplace transform of something and we don't know where to start, we'll go ahead and start with the definition. And in this particular case, we're going to use integration by parts, where u is given by e to the minus st, and dv is given by x prime of t dt. So expressing our integrand as u dv, we can apply integration by parts, which tells us that that the integral of u dv, of course, is u times v. So here's the expression u times v, minus the integral of v du. So of course v du is here. So this is v and du in this case. Okay. Now, of course, we can manipulate those first terms. The first terms look like e to the minus sb times x of b minus e to the minus s times 0 times x of 0. So we get this x of 0. And then we see what happens here is that this integral begins to look a little bit like the definition of the Laplace transform of x. Now, what we need here is we need our function x to be nice, that is of exponential order and piecewise continuous. And when it is, it turns out that this first term goes to 0 as b goes to infinity. So when this term goes to 0 as b goes to infinity, what we're left with is just x of 0, and we're left with this integral involving e to the minus st and x of t, which actually is the Laplace transform of x. Okay, so here is that definition, namely that the Laplace transform of x prime is given by s times the Laplace transform of x minus x at 0. We can use that definition actually to find the Laplace transform of the second derivative too. So to find the Laplace transform of the second derivative, we'll just go ahead and use the above property twice. So here is applying that property once, right? The Laplace transform of the second derivative should be s times the Laplace transform of the first derivative minus the first derivative at 0. And then we can go ahead and evaluate the Laplace transform of the first derivative here. Okay, so just an iterative process here, finding that the Laplace transform of the second derivative turns out to be s squared times the Laplace transform of the 0th derivative minus s times x at 0 minus x prime at 0. Okay, so we can see the Laplace transform of both derivatives involve the Laplace transform of the function and then some initial values, some values of the function at 0. So just to sort of recap here, so long as our function x is nice, which ours always will be, we can express the Laplace transform of the first derivative in terms of s and the Laplace transform of the function, the Laplace transform of the second derivative in terms of s squared and s, and the Laplace transform of the function. And even though we won't use this, you can imagine that the Laplace transform of the nth derivative similarly involves a factor of s to the n power and a whole bunch of those derivatives. So a couple examples using the Laplace transform of the first derivative. Here we'll go ahead and use a derivative identity to find the Laplace transform of t squared. So I'll remind you of that derivative identity. The derivative identity is here. And in this case, we'll just take f of t equal to t squared. We know that when f of t is t squared, f prime of t is 2t. So here is that derivative identity with f of t and f prime of t plugged in. Now we can use linearity and the property of given the Laplace transform of s squared, and just solve algebraically here for the Laplace transform of t squared. So that Laplace transform of t squared is 2 times the Laplace transform of t divided by s, which is 2 over s cubed, as it turns out. One can use this iteratively and the principle of mathematical induction to derive the Laplace transform of t to the n as n factorial times divided by, the s to the n plus 1 power. Okay, so this is where that one entry in our chart comes from. We can similarly use our derivative identity on a function which we already know how to find the Laplace transform of. So here is the derivative identity to find the Laplace transform of the exponential function. So again, here we'll take f of t to be e to the kt. Then of course f prime of t is k e to the kt. So this expression is just our derivative identity using f of t equals e to the kt and f prime of t equals k e to the kt. Solve algebraically using linearity for the Laplace transform of e to the kt, and we get the expected value here, which turns out to be 1 over s minus k. Okay, similarly, you can imagine that the Laplace transform of the second derivative can be used to find the Laplace transform of sine and cosine, since those are related by a second derivative. So I'll let you play with that, but that's another thing we can do. Okay, so finally at long last here, we're ready to solve some initial value problems. And as I mentioned before, sort of our usual strategy for solving an initial value problem is using the transform, then obtaining an algebraic equation for the transform of the unknown function, finding the solution of that algebraic equation, then using the inverse transform. So I like to think of that process in the following diagram. Again, given an initial value problem for an unknown function x, we can transform that initial value problem to identify an algebraic equation, solve that algebraic equation for the transform solution, and then use the inverse transform to identify the solution of the initial value problem. Okay, so a few examples. Here's the first one. The initial value problem 2x prime plus x is 0, where x of 0 is given by 1/2. So we'll start off by transforming the initial value problem. The transform of the left-hand side turns out to be just 2s plus 1 minus, 2s plus 1 times x of s minus 1. Of course, the transform of 0 is 0, so that those two things ought to be equal, right? The transform of the left-hand side should equal the transform of the right-hand side. Okay, so here's what the transform solution satisfies. This is the algebraic equation for the transform solution, which we can pretty quickly solve for the transform solution x of s. Now all that's left is to identify the solution of the initial value problem by finding the inverse transform of this function. If this is feeling familiar to you, we found the inverse transform of this function in a previous video, which turns out to be 1/2 times e to the minus t over 2. And that's the solution to the initial value problem. Okay, second example. Here's a second example. Let's solve the initial value problem x prime plus 6x equals e to the 4t, where x of 0 is 2. So again, we'll go ahead and transform the initial value problem, the left and right hand sides. So using again our derivative identity here, the left hand side transforms like s plus 6 times x of s minus 2. And of course the right hand side transforms like 1 over s minus 4. Okay, so of course the transform of the left hand side should equal the transform of the right hand side, and that gives us an algebraic equation for the transform solution. So here's an algebraic equation for the transform solution that we can solve pretty quickly. For the transform solution, just solve algebraically. Okay. Again, all that's left is to use the inverse transform to identify the solution of the initial value problem. And once again here, we've actually found the inverse transform of this function in a previous video using a partial fraction decomposition. So that ends up being this combination of exponentials and of course the factor 2s plus 6 transforms like 2e to the minus 6t. Okay, so again, the details on that are in a previous video. Another example here is the initial value problem x prime plus x is 2 cosine of 2t, where x of 0 is 0. Again, we'll go ahead and transform the initial value problem. The left-hand side transforms like s plus 1 times x of s. The right-hand side transforms like 2s over s squared plus 4. Those ought to be equal, giving us an algebraic equation for the transform solution. Solve that algebraic equation for the transform solution, and we find this expression that the transform solution is 2s over quantity s plus 1 times s squared plus 4. If you're having a deja vu moment again, yes, you're right. We have found the inverse transform of this function too. It requires a partial fraction decomposition, and again, we did that in a previous video, and the solution ends up being this combination of e to the minus t, cosine of 2t, and sine of 2t. Okay, this is the solution of the differential equation. Okay, finally, a couple examples where we see the power of the Laplace transform to deal with piecewise continuous sources. Again, back to our sort of general form here, we're really interested in cases where this function f of t is piecewise continuous. Okay, so the Laplace transform ends up being pretty powerful in this case. Okay, so here's the first example. An initial value problem given by x double prime plus 4x is sine of t minus heavy side of t minus pi times sine of t. So you can think about this right-hand side as a forcing function that is sine of t from 0 to pi, and then we turn off that forcing function so that it's actually 0 after t equals pi. The left-hand side we can sort of think of as an undamped mass spring system here, right, with 0 initial conditions. Okay, so we're getting this mass spring started from rest at its equilibrium position by forcing it with a function sine of t, and then we'll look at how the response is after we turn that forcing function off at t equals pi. Okay, so the first observation here is that we can express the heavy side function t minus pi times the sine of t actually as minus the heavy side function of t minus pi times sine of t minus pi. And it's important to do this because what we're going to want to do here is use our property that that we know how to transform things that look like the f of t minus a times the heavy side of t minus a. Okay, so we want to make sure that our sign is translated appropriately in order to do that. Once we do that, though, we can proceed as we've done before by having a look at the transform of the left side, the transform of the right-hand side, and setting those equal, right? So the transform of the left-hand side should equal the transform of the right-hand side. Of course, these initial conditions are 0, So we can see then that the transform solution satisfies sort of a complicated equation, but an equation nonetheless where we have some term involving s squared plus 1 and s squared plus 4. Okay, so when you stare at this, you should see a couple of things here, right? You should see this term involving s squared plus 1 and s squared plus 4 that you know you're going to have to decompose. And then you should see this other term involving e to the minus pi s times s squared plus 1 and s squared plus 4. Okay, so that term, as it turns out, should remind you of e to the minus as times f of s. Okay, and we know that when we have terms that look like e to the minus as times f of s, those terms will invert. The inverse transform will involve a switching property. Okay, so the key here is that in both cases we're going to have to find the inverse transform of this function f of s, which ends up being this combination of 1 over s squared plus 1 and 1 over s squared plus 4. So there's a partial fraction decomposition here that you can find, so I'll just have you verify this, but it turns out that the partial fraction decomposition is 1/4 times 1 over s squared plus 1 minus 1 over s squared plus 4. And the two terms in that partial fraction decomposition should remind you of Laplace transforms of sine of t and sine of 2t respectively. Now, of course, there's a constant multiple that we'll need to deal with here that we'll get back to in just a second. Okay, so in any case, the transform solution can be expressed in the following manner, using again the partial fraction decomposition. Okay, so this should remind you of f of s, and again, it turns out that this is the same f of s times e to the minus pi s. So this is where that switching property will come into play. Okay, so the inverse transform therefore gives us the following, and those two terms again come from 1 over s squared plus 1 gives us things that look like sine or a switched on sine, and 1 over s squared plus 4 gives us a sine of 2t and a switched on sine of 2t. Okay, just for a little bit further exploration, we can go ahead and have a look at the graph. So you can see here that something interesting happens at pi, where suddenly the response changes and the amplitude changes, and we're left in sort of a steady state there involving that response. Okay. One more example involving an RC circuit. So here is an RC circuit. Find the charge Q of T on an RC circuit that has a resistance of 1 ohm, a capacitor of 1/3 farad, where the 1 volt battery source is on from 1 to 2. That is a square pulse, and here we're given 0 initial charge on the capacitor. Okay, so we'll re-express this function as an initial value problem. Again, r q prime plus 1 over c times q is f of t here. F of t is the source or the battery, okay, where q of 0 is given by 0. The source term, this square pulse, can be represented as a combination of Heaviside functions here. The square pulse is on at 1 from t equals 1 to t equals 2, and then it turns off. Okay, so we can go ahead and just proceed transforming the initial value problem using c equals 1/3, and f of t is the difference of those Heaviside functions. So the transform of the left-hand side ends up being s plus 3 times capital Q of s. And the transform of the right-hand side, just using the transform of those Heaviside functions, involves a term that has e to the minus s and a term that has e to the minus 2s. Okay, so here's the transform solution. The transform solution is has left-hand side equal to right-hand side, and it's, again, pretty quick to solve that algebraic equation for the transform solution, which we've done here. Okay, so we can see that each term involves some function f of s times e to the minus s, and also f of s times e to the minus 2s. Okay, so once again, in this case, that f of s turns out to be 1 over the quantity s times s plus 3. Okay, so we know we're going to have to find the inverse transform of that to be able to use the switching property. Again, here are e to the minus s and e to the minus 2s indicate switching properties. So a partial fraction decomposition, which again I'll invite you to verify, tells us how to find the inverse transform of that. So here you should see something that looks like the transform of 1 over s, and the transform of e to the minus 3t, which is 1 over s plus 3. Okay, so so with this sort of as our base inverse transform, we can go ahead and switch that at t equals 1, and then switch it again at t equals 2. Okay, so here's what the inverse transform gives for the solution. Again, a switching property at t equals 1, and a second switching property at t equals 2. Okay, so the graph of this function looks exactly like you would expect it to, with the initial condition of 0 charge on the capacitor and the battery off. Nothing happens. When the battery turns on at 1, the charge on the capacitor starts to ramp up, and then when the battery turns off at 2, that charge just decays away. Okay, so pretty cool graph of the solution. Kind of looks like a shark fin, which I like, and a pretty cool use of the Laplace transform and those switching properties to incorporate that graph. Okay, hope you've enjoyed solving some initial value problems using the Laplace transform. In this video, again, we saw how to find the transform of a derivative, saw some properties of the transform of the derivative, and then we solved a whole bunch of initial value problems, including some where the source term is a discontinuous function. So long for now, and we'll see you next time. Bye-bye.